We started our design solution by researching problems related to agriculture and runoff. While researching runoff, we found out that it can pollute water greatly and that the water polluted is harder to use for us and animals alike. This results in habitat loss for animals that live nearby, fish to eventually start dying off, and water that is no longer available to drink without the risk of becoming sick. While people have started creating solutions to help solve runoff, or at least reduce it, there hasn't been a great solution in this issue. Next, we look to nature to solve the runoff pollution. We researched common pollutants of pesticides and insecticides and found arsenic to be the most harmful. Long-term exposure to arsenic from drinking water or food preparation can cause serious illness over time. Arsenic has no odor or taste, which makes it especially dangerous for people who are unaware of its presence. Narrowing our sights to arsenic, we found some natural water filters that was able to filter arsenic out of the ground like the fern. Now the fern soaks the arsenic out of the ground through its roots like a straw. The fern's root system's and absorption capacity allows it to soak up large amounts of arsenic without becoming damaged. This helps it act as a natural water filter by soaking in arsenic and cleaning water nearby. After contaminated water is soaked in, it moves through the roots to the leaves. Then a special encoded protein moves through the water and separates the arsenic into the vacuoles of the plant cell, which is the equivalent of a trash can. Ferns then turn the separate arsenic into biomilk. After gathering this information, we used it to bring us to a design solution. At first, we thought about how we could soak up water similar to the fern's roots, and we looked to the sponge. Sponges are known to soak up water and hold it, so we planned on using this to soak in water where it would be then filtered by something else for arsenic. After we soak up the water, we use iron oxide nanoparticles that act as a magnet with arsenic. Arsenic is attracted to the nanoparticles, so they separate from the water and become saturated in the nanoparticle. The nanoparticles will be about 5 nanometers in diameter and have an absorption capacity of 95 milligrams per gram or 47 milligrams per gram respectively, so that they can't leave the membrane. The membrane of our model would contain nanoparticles inside that acted as a filter. These nanoparticles would attract arsenic from inside the water and separate it from it. First, the contaminated water would enter from the front, then it would come in contact with the nanoparticles in the membrane where it would take in arsenic before leaving through the back. Our product will be anchored so that it can't move through the stream. It will be held by a cutout in the soil where the product was placed inside. As explained before, water will travel through the sponge, interact with the nanoparticles, and become separated. Then the clean water will travel through the backside of the sponge and continue to flow downstream.